Welcome to Creata classes. This is second lecture under the altitude series. In this lecture, we will cover the orthic triangles. In the previous lectures, we have covered the altitudes and the orthocenter. Let's take a triangle ABC. Here AD, BE and CF are the altitudes for this triangle. AD, BE and CF are perpendicular to the respective sides. So in the previous lecture, we have seen that these three are the altitudes and the intersection point of these three altitudes is the orthocenter. Here the point H is the orthocenter for the triangle ABC. And in this lecture, we will cover the orthic triangles. So first of all, let's see what is the orthic triangles. Orthic triangles are the triangle formed by joining the foot of the altitudes. Here point D, E and F are the foot of the altitude AD, BE and CF respectively. So a triangle which is formed by joining these three foots of the altitude is known as orthic triangle. So for this triangle ABC, the triangle DEF is the orthic triangle. In this lecture, we will see the various properties of the orthic triangle and we will derive the various formulas related to the orthic triangles. So we have got the basic introduction to the orthic triangles. Let's proceed further to the various properties of the orthic triangle. So for this triangle ABC, the triangle DEF is the orthic triangle. If we take the triangle ABE, here angle E is 90-degree angle because BE is the altitude for the side AC. This angle is angle A. So can we say angle ABE is equal to 90-degree minus angle A? Why? Because we have applied the sum angle property of the triangle. That is the sum of three angles of the triangle is 180-degree. Angle E is 90-degree. Angle A we have taken as angle A and we have got angle B as 90-degree minus angle A. Similarly, if we take the triangle AFC, this triangle, here angle F is a 90-degree angle and this angle is angle A. So can we say angle ACF is equal to 90-degree minus angle A? So we have got both of these angles as equal to 90-degree minus angle A. Means both of these angles are equal to each other. Got it? Moving further, in the previous lecture, we have discussed about the cyclic quadrilateral. That is, we have seen that a triangle with the altitude can have 6 cyclic quadrilaterals. There we have discussed that BDHF is a cyclic quadrilateral and also DCEH is also the cyclic quadrilateral. I am just repeating the same fundamental again. If we take BDHF as a quadrilateral, here angle D and angle F both are 90-degree angle. That is, angle D plus angle F is equal to 180-degree. And we know the property of the cyclic quadrilateral, that is the sum of opposite angle is 180-degree. So we got BDHF as a cyclic quadrilateral. Similarly, we got DCEH also as a cyclic quadrilateral. Here angle D and angle E are 90-degree angle. So angle D plus angle E is equal to 180-degree. So both of these are cyclic quadrilateral. This is the fundamental that we have covered in the previous lecture. Let's come back to our main lecture on the orthic triangle. Okay, we are back. Here also the same fundamental will be applicable. That is, these two quadrilaterals will be the cyclic quadrilaterals. Got it? Let's take the first cyclic quadrilateral, that is BDHF. Here if you observe, the chord FH is subtending the angle at point B and also at the point D. And as per the property we have done in the circle, the angles subtended in the same segment of a circle are equal to each other. So we can say angle FBH is equal to angle FDH. And just now we have seen angle FBH is equal to 90-degree minus angle A. So we got FDH as also equal to 90-degree minus angle A. And if we take the second cyclic quadrilateral, that is DCEH, here also we can apply the same fundamental. that is the chord HE is subtending angle at point D and point C, and both of these angles will be equal to each other. Got it? And just now we have seen angle HCE is equal to 90 degree minus angle A. So can we say angle HDE is also equal to 90 degree minus angle A? Okay, both of these angles will be equal to each other. Got it? If you observe, all of these four angles are equal to 90 degree minus angle A. Here if you observe, both of these angles are equal to each other. So can we say the line AD is the angle bisector of angle FDE? Here the line AD is bisecting this angle into equal parts, that is 90 degree minus angle A. So AD is the angle bisector. Similarly, we can prove BE is the angle bisector of FED and CF is the angle bisector of DFE. So we got these three line segments are angle bisector of these three angles. Further, if we take these three line segments that are the angle bisector and this triangle DEF out of the figure, can we say these three line segments are angle bisector for this triangle DEF? And we have seen that the intersection point of three angle bisector is the incenter. So we got point H is the incenter for the triangle DEF. And just now we have also seen the point H is also the orthocenter for the triangle ABC. So we got that the point H is also the orthocenter of the triangle ABC, and also the point H is the incenter for the triangle DEF. Got it? This is the property of the orthic triangle. That is, the incenter of the orthic triangle is equal to the orthocenter of the main triangle. Got it? This is very important property. Let's move further to the next fundamental. In this fundamental, we will calculate the sides of the orthic triangle as well as we will see the various angles of the orthic triangle. Here in this figure, ABC is the main triangle and DEF are the foot of the altitude AD, BE and CF respectively. So we can form a triangle with the foot of the altitudes. That triangle is the orthic triangle. So the triangle DEF for this triangle ABC is the orthic triangle. In this figure, we will try to calculate the angles of this orthic triangle DEF as well as we will try to find the sides of the triangle DEF, that is DE, EF and FD. Let's see how we approach this fundamental. Just now we have proved angle FDA is equal to 90 degree minus angle A and also angle ADE is equal to 90 degree minus angle A. So on adding, we got angle FDE, that is this complete angle, as 180 degree minus 2 times angle A. So we got angle D. Similarly, we can say angle E is equal to 180 degree minus twice of angle B, and angle F, that is angle DFE, is equal to 180 degree minus twice of angle C. These are the three angles of the orthic triangle: angle D, angle E and angle F. So we got the three angles of the orthic triangle. Now we will see the three sides of the orthic triangle. Many fundamentals will be used in deriving the sides of the orthic triangle, so your close attention is needed. Let's proceed. First of all, let's check the triangle AFE. We have taken this triangle. If we apply the sine rule, can we say FE upon sine A is equal to 2 times R1? Here R1 is the circumradius for this triangle AEF. We have denoted the circumradius as R1. And we have applied the sine rule, that is A upon sine A is equal to 2 times R. Here the side A we have taken as FE. So FE upon the sine of opposite angle, that is sine A, is equal to 2 times the circumradius. We have applied the simple sine rule. Further, in this figure, can we say the quadrilateral AFHE is a cyclic quadrilateral? Here angle F and angle E both are equal to 90 degree. So we got the sum of opposite angle of this quadrilateral is equal to 90 plus 90, that is equal to 180 degree. So we got this quadrilateral, that is AFHE, as a cyclic quadrilateral. So the circle around this quadrilateral is also the circumcircle for the triangle AFE. A circle which is passing through the three non-collinear points is unique to those 3 points. So we can say no other circle can pass through the point AFE. So we got the circumcircle for the triangle AFE is same as the circle around the cyclic quadrilateral AFHE. Got it? Further, if you observe, AH is the diameter for the cyclic quadrilateral AFHE, and this line segment is also the diameter for the circumcircle for the triangle AFE. So can we say AH is equal to twice of R1? Twice of R1 is the diameter, that is 2 times the radius is the diameter. So we got AH is equal to 2 times R1. Slightly tricky fundamental, we are comparing the circumcircle of the triangle AFE with the circle of the cyclic quadrilateral AFHE. Both the circles are same, so we can say the diameter of the cyclic quadrilateral is same as the diameter of the circumcircle, and the diameter of the circumcircle is the twice the circumradius. Okay, diameter is twice the radius, so we got AH is equal to 2 times R1. So let's replace 2R1 in the first equation with AH. We got FE is equal to AH into sin A. Further, in the previous lecture, we have calculated the distance of vertex to the orthocenter. There, we have seen that AH is equal to 2R cos A, and BH is equal to 2R cos B, and CH is equal to 2R cos C. We have done the same in the previous lecture. So, can we replace AH with 2R cos A? Let's do so. We got FE is equal to 2R cos A into sin A. Now we are having two options. We will take the two path. In the first path, we will replace 2 sin A into cos A with sin 2A. This is the formula of trigonometry, that is sin 2A is equal to 2 times sin A into cos A. On replacing, we got FE is equal to R times sin 2A. And in the second option, that is the second path, we will apply the sine rule, that is 2R is equal to A upon sin A. So we got 2R into sin A is equal to A. On replacing the terms, we got FE is equal to A times cos A. So we got the two formula of FE, that is the side of the orthic triangle, as FE is equal to A times cos A, which is equal to R times sin 2A. So this is the formula of the side of the orthic triangle. In the similar way, we can calculate the value of FD, that is again the side of the orthic triangle, as B times cos B, which is equal to R times sin 2B. Similarly, ED is equal to C times cos C, which is equal to R times sin 2C. Got it? So we have got the angles of the orthic triangles as well as we have got the sides of the orthic triangle. So these are the formulas of orthic triangle. Let's move to the next fundamental. The next fundamental is orthic triangle has the smallest perimeter of any triangle with vertices on the sides of the triangle ABC. As per this fundamental, if we take the triangle ABC, this is the triangle ABC, we can form many triangles inside this triangle ABC which is touching the three sides of the triangle. We can form infinite number of triangles inside this triangle. All these triangles are touching the sides of the triangle ABC. Now the question is, out of all these triangles, which triangle is having the smallest perimeter? The fundamental is that out of all these triangles, only the orthic triangle will be having the smallest perimeter. Got it? Orthic triangle has the smallest perimeter of any triangles with vertices on the sides of the triangle. Now we will prove the same. The proof is very interesting as well as slightly tricky. Your imagination is required. So with the help of animation and the visual tools, I will try to make you visualize the concept as well as the basic understanding behind the fundamental. Hope you will enjoy the same. Let's see. First of all, let's check the triangle ABC. This is a triangle ABC. Let's draw a random triangle DEF inside this triangle ABC, touching the three sides of the triangle ABC. This is the random triangle DEF we have drawn. We have to prove that the triangle which is having the minimum perimeter or the smallest perimeter will be the orthic triangle. Let's do so. First of all, let's reflect FD about AB. This is AB and this is FD. We have to reflect this line segment FD about AB. Here AB is the mirror and we are reflecting FD about AB. We got FD dash. What we have done, we have reflected the point D as D dash about AB. We got FD dash. Here FD dash is the mirror image of FD. So FD dash and FD will be equal to each other. Similarly, if we reflect ED about AC, we got ED double dash. Here also ED is equal to ED double dash. In this fundamental, we have to focus on the perimeter of the triangle DEF. So firstly, let's calculate the perimeter of this triangle DEF. That will be FD plus DE plus FE. That is the sum of the three sides of the triangle. So we have to calculate the minimum perimeter. That is minimum of FD plus DE plus FE. Further, can we replace FD with FD dash and ED with ED double dash? Okay, the same we have just calculated. So we got the perimeter of this triangle as FD dash plus E double D dash plus FE. So this is also the perimeter of the triangle DEF. Perimeter is the total length of the boundary. So if we refer the figure, here D dash F and FE and ED dash is this complete path. This path will reflect the perimeter of the triangle DEF. So the minimum perimeter will be the minimum distance between point D dash and D double dash. This complete path is the perimeter and the minimum perimeter is the shortest distance between the point D dash and D double dash. And we know the shortest distance between any two points is the straight line. So can we say the line segment D dash D double dash means this line segment is the shortest distance between the point D and D double dash? We can say so. That is the shortest distance between any two points is the straight line. So here the line segment D dash D double dash is the smallest perimeter. Further, let's join AD dash, A double D dash and AD. Okay, we got the three line segment. Are you able to observe here line AD dash is the reflection of line AD about AB. Here AB is the mirror. Previously, we have taken the point D dash as reflection of point D about AB. So we can say AD dash is the reflection of AD about AB. Got the point? So we can say AD is equal to AD dash. And similarly, we can say AD is equal to AD double dash. If we compare these two equations, we got AD is equal to AD dash, which is equal to AD double dash. Means all these three line segments are equal to each other. If we take the triangle A, D dash, D double dash means this triangle, its two sides are equal, that is both of these sides are equal. So can we say this triangle is an isosceles triangle? The triangle with two sides as equal to each other. So coming back to our fundamental, that is somehow we have to get the distance D dash, D double dash, as this is the minimum distance between the point D dash and D double dash. So we are calculating the shortest distance between D dash and D double dash. Further, as this triangle is an isosceles triangle, so if we reduce these two equal sides of the triangle, can we say the third side, that is the base of the triangle, will automatically get reduced? These two equal sides, if we are reducing, the base is automatically reducing. More we will reduce a d dash and a d double dash, more the d dash d double dash will be reduced. Getting the point? So till now we are finding the shortest distance between d dash and d double dash. So now our focus has been changed to find the shortest length of a d dash and a double d dash. Shorter these two lengths will be, the shorter will be the d dash distance. And just now we have seen that AD dash and AD double dash is equal to AD. So we need to get the shortest distance of AD. Shorter will be the AD, so we will get the shorter AD dash and AD double dash. All these three lengths are equal to each other. So the shorter will be these three lengths, the shorter will be the length D dash D double dash. Are you getting the point? Are you able to see the transformation? I am just repeating again to remove any of the confusion. The perimeter of the triangle is DF plus DE plus EF, and we have replaced DF with D dash F and ED with ED double dash. This path is reflecting the perimeter of the triangle DEF, and here we have to find the minimum perimeter of the triangle DEF. So to find the minimum perimeter of the triangle, we have to find the shortest distance of this path. And the shorter distance is D dash D double dash. And we have also found that D dash D double dash is also the base of an isosceles triangle AD dash D double dash. These two sides of the triangle are equal to each other. The more we will reduce these two equal sides, the more will be the base, that is D dash D double dash is reducing. So we understand that for getting shortest D dash D double dash, we have to find shortest length of these two equal sides of the triangle. And these two sides of the triangle are equal to AD. This line segment is the AD. So finally, we understood that the minimum perimeter of the triangle can be achieved where AD is the shortest. Okay, getting the point? This concept is slightly tricky, so your full attention and understanding is required. Means we will get the smallest perimeter of the triangle DEF by getting the shortest length of AD. So the triangle ABC with the shortest AD will have the minimum perimeter of the triangle DEF. And we know the shortest distance between the point and the line segment is the perpendicular distance. So we can say the AD will be minimum at the point where AD is perpendicular to BC. Are you getting this point? AD can be anywhere on this line segment. Any of this line segment can be AD. And we have to find the shortest AD. The AD will be shortest at the point where it is perpendicular to the line segment BC. Getting the fundamental here? So the smallest perimeter of the triangle DEF will be possible only when AD is perpendicular to BC. That is, AD is the altitude for the triangle. We got AD as the altitude of the triangle. That is, point D is the foot of the altitude. And we know the triangle formed by the points at the foot of the altitude is the orthic triangle. So we got the triangle DEF is the orthic triangle. That is, the orthic triangle has the smallest perimeter of any triangle with vertices on the sides of triangle ABC. The orthic triangle will have the smallest perimeter inside the triangle ABC. The fundamental is slightly tricky, but I hope you are able to understand the concept. So that's it for the orthic triangles. We have covered all these formulas. Hope you have enjoyed it. So thank you very much for being with Creata classes. And one thing, no need to write down the formulas. All these formulas are available in the download section. Okay, just go to the download section and download the PDF of the formulas. So thank you very much for being with Creata classes. Bye for now.